You're older, you go to the same.
That was kind of a barrier. I was always like,
All right, good evening, everyone. Let's go ahead and get started. I thought I might have to go a third time. As a teacher, you always know it takes 3 times to get the class quiet down. So good evening, everyone. And I'd like to just say thank you for coming tonight and joining us at this inaugural event of the Casper College Community Learning Series. My name is Brandon Cosine, and I currently serve as the president of Casper College, and it's my privilege to welcome you to this gathering. This series was born out of the many discussions and questions I've heard in the community by our concerned citizens. It is designed as a forum for learning, questions, and discovery. As a community college, part of our mission is to bring people together to explore important topics in a spirit of curiosity and respect. We believe in the power of education to spark new ideas, broaden perspectives, and help us understand the world more deeply. This is an academic setting, and with that comes a commitment to fact-based information and inquiry. That means our discussions here are grounded in evidence, research, and knowledge, not personal opinions, partisan politics, or ideological debates. While those have their place in our other venues, our role here is to provide clarity, promote understanding, and encourage thoughtful exploration. We also want to emphasize that inquiry is at the heart of education. Asking questions, seeking better understanding, and wrestling with complex issues are part of our mission as a community college, to be a hub of knowledge, dialogue, and lifelong learning for everyone in our community. We're so glad that you are here. We'll be asking you for your feedback at the end of this evening to help us decide and help us craft future topics for the learning series as well. So I ask that you please make sure that you scan the QR code that Shauna Trujillo has around here and give us your feedback on the session, because this is not a one and done type event. This is going to be a year-long series. So again, please give us your feedback. And I would like to introduce now our speaker for this evening. His name is Wayne Hiley, and he is a metallurgical engineer. I even practiced that. Metallurgical engineer with a minerals processing emphasis, and has dedicated his 35+ year professional career to the U.S. uranium recovery industry, the front end of the nuclear fuel cycle. He has held various processing, engineer, management, and executive positions at companies pursuing both uranium production, and has overseen the design, licensing, construction, commissioning, and ramp up of various projects. He is presently semi-retired and provides consulting and advisory services to the uranium recovery industry. In his professional capacity, Wayne has developed a deep understanding of radiation safety, industrial safety, environmental stewardship, and the regulatory framework in place for the protection of the environment and surrounding communities when nuclear projects are proposed. He is a lifelong member of the Society of Mining, Metallurgy, and Exploration, and has served multiple terms as the officer of the Central Wyoming Section ODSME. He has also served on the board of the Wyoming Mining Association. He is past president of the Uranium Producers of America. Wayne and Stacy Hiley have resided in Casper, Wyoming for over 28 years and have raised 3 children here. Wayne has been active in the community as a Rotarian, city councilman, scout leader, and board member of the Platte River Trails Trust. He's in my Rotary group, and he's just a good dude. So please welcome Wayne Hiley.
Brandon, whatever you've done, if the future of this series goes like tonight, you got something going that was really needed in the community. I'm really pleased to be here to share some thoughts with you about the nuclear industry, and I'm so glad that you came here to listen. Yesterday in the newspaper, I was reading an article or an opinion piece or something, and it concluded with, we have a real need for real, honest public engagement to demystify the nuclear industry. Well, that's really what I wanted to do when I agreed to this presentation, is to help demystify radiation, to help people understand radiation safety aspects, the nuclear power industry, how it's so similar to every other power industry and how it varies a little bit. And, just a number of things. But why do we have this conversation going on? Because the table is full of nuclear opportunities for the state of Wyoming. So I have a couple slides up front, just to set the stage, set the table. Look, in 2024, TerraPower started construction of the Natrium Advanced Reactor Demonstration Program in Kemmerer. So we have a project, a nuclear demonstration project happening now in Western Wyoming. Back in 2021, when that was announced, there were 4 communities competing for the opportunity to have TerraPower come to theirs, and Casper and Glenrock was one of those communities together. We were competing for the opportunity to have that demonstration plant in our neighborhood because of the jobs and the economic growth. Recently, we've heard from a company called BWXT or BWX Technologies. There's over 100,000, I think they're a Fortune 200 company, 100,000 employees at BWXT. They're a significant player in the nuclear industry, and they want to locate facilities in Wyoming. Now, over the, again, very recent developments, but they made it clear they'd like to put a nuclear fuel manufacturing facility in Gillette. They also want to do a micro reactor development. I don't talk a lot about that in my presentation, but I know about it if you have questions. It's called the Banner micro reactor. It would produce about 50 megawatts of electricity, and they want to tie it in with one of the soda ash production facilities in Green River. I think that's really cool. And in Wyoming already, we have the Radiant Industries in our backyard talking about a portable micro reactor manufacturing facility. That's probably what has a lot of people interested. I'll disappoint because I'm not speaking directly about that throughout the presentation. I'm speaking indirectly about safety aspects of the nuclear industry. But if we want to have that dialogue, that may happen. Already Wyoming, and the reason I'm here for the last 28 years is that we have an established uranium mining industry, and it is growing. It is growing now, and the uranium mining industry is probably healthier than it's been in the entirety of the 28 years that I've spent in Casper. So if this goes well for the companies that are interested in coming here, we'll have more opportunities and we'll have more discussions about hosting nuclear fuel cycle type facilities in our neighborhood. Why all the growth? Because nuclear power right now already produces about 20% of our nation's electricity. So 1 in 5 light bulbs, 1 in 5 homes is powered by nuclear in our nation. And it's been that way for many, many years, safely operating. The nuclear power generation is carbon free, and that's an attribute that I think many, many people are drawn to nuclear for. It's a carbon free source of electricity, and it has actually truly an incredible safety record in the United States. So I'm putting up a slide that I find very compelling. This comes from an outfit called Our World in Data, but it asks the question, what are the safest and cleanest sources of energy? And it presents the death rate from air pollution and accidents per terawatt hour of electricity generated. Terawatt's just a lot of watts, don't worry. It's a lot. It is a lot. And it also presents greenhouse gas emissions by energy source. And you can see, and I'm not here to dip poll or anything else, because I'm truly, in my heart of hearts, believe that we need everything to power our nation right now. We're going through an unprecedented growth rate and demand for electricity in our nation as our economy grows and as the internet and the advanced technologies grow. We're going to need more electricity than we can figure out how to produce. So this isn't about somebody making somebody a bad guy and somebody a good guy. it's just the statistical facts of the situation. Right now, coal presents 24.6 deaths per terawatt hour of electricity generated. Nuclear, on the other hand, presents 0.03 deaths. So 24.6 versus 0.03. That's somewhere around 1,000 times, 1,200 times higher for coal. Oil's not so far behind. It's 18.4 deaths. Wind, solar, and nuclear all enjoy a very good safety record, as does hydro. But more of these are attributable to air pollution than they are industrial accidents, and I think that's something you need to know. And also, because you can't really read the fine print, I doubt, unless you're sitting right in front on this screen, which is beautiful. The nuclear energy deaths do include deaths attributed to the Fukushima and Chernobyl accidents, which we've all heard about. So, and there were no deaths attributed to 3 Mile Island. So, those deaths are included in this statistic. And then on the greenhouse gas front, we have 970 tons of greenhouse gas emitted for. This is per gigawatt, a little smaller number than a terawatt per gigawatt of hour of electricity generated. 970 tons, 720 tons for our gas, and 440 for natural gas, or oil and natural gas. So those, we all know that they're greenhouse gas emitting carbon based fuels. Nuclear life cycle attributes 6 tons. So again, 160 times higher attribute of greenhouse gas emissions for coal than for nuclear. And I think that's what's compelling about nuclear, is it's clean, it's green, and it's safe. The other thing that my friends all say, this is the most incredible thing, Wayne. This is it. I mean, one uranium fuel pellet, which is about 1 inch long, and you can hold it in your hands like you see here, has the energy equivalence. It's of 17,000 cubic feet of natural gas, or 120 gallons of petroleum oil, or a ton of coal. So, one little uranium pellet, a gram of uranium in a fuel pellet, the energy density is so incredible that, this is why nuclear facilities have small footprints and small waste footprints. It's because of the energy density contained in uranium. So if we did have these proposed facilities come, really, what's the economic benefit to Wyoming? Really, it's a growth in a new manufacturing industry. I think I read we have 10,000, maybe 13,000 manufacturing jobs in the state right now. And TerraPower proposes to add 250 permanent to 400 permanent jobs. BWXT talked about 200 permanent jobs in Gillette. But if they did the other demonstration plant or in Green River, you're talking another 200, something like that, more jobs. So 200 to 400 jobs for BWXT, and Radiant has publicly stated 250 jobs. Sum total, about 1,000 jobs, or 10% growth in our manufacturing base in the state of Wyoming for jobs. And those are jobs that people like me who raise their children here love to see. I want to see opportunities for my children and your children and grandchildren to stay here. I have 3 kids. I'm blessed that they're all in the state. And I have 3 grandchildren who are going to need jobs. And, as long as they're here, I'm here. Okay. So you're stuck with me because right now they're here. They're working, they're productive, and members of society. And it's a great opportunity for us. But it's also an opportunity for our state to gain additional Wyoming uranium mining jobs. The mining industry a couple of years ago, probably 200 people working. Now I guess we're 500-600 people in the state. There's exploration, there's project development. All my friends, you heard I'm semi-retired, right? Which means I'll consult if you give me enough. Otherwise, I'm content to sit on my duff and do things like this. All all my friends are complaining about how hard they're working now. And I said, well, you have a choice. You could do what I did. Anyways, so it's a great time. All that is just context and really what I wanted to do. You know, again, we're into some fact-based learning and I wanted to condense some information about what I know and what I've learned in my career into something that's understandable. So this is the Nuclear 101 portion. Let's get some STEM education going here in this room tonight. I want to address the questions. What is the nuclear fuel cycle? How does a nuclear power plant work? What is radiation? How do we protect against it? And then what exactly is spent nuclear fuel? And is it safe to keep around and be around? So those are the topics that I thought I would spend a few minutes on. And again, thank you for patiently sitting and listening, because I know that the way this schedule works, if I speak for 30 minutes, and that won't be hard for me to do. If you ask questions, I won't be done in an hour. So we're going to try and hold questions to the end. If you have a notepad or a means of keeping your questions, we'll get to them, I promise. But this is a lot of topic, and I think we're moving along pretty well. One slide on the nuclear fuel cycle, because really what we're talking about is attracting jobs across the nuclear fuel cycle. Been in the state long enough. When I first arrived, everybody said my mom, my dad, my grandpa, my brother worked in Shirley Basin. They said, Wayne, when are we going to get Shirley Basin back up and going, producing uranium? I'm pleased to tell you that the company that has that project now, UR Energy, is developing a new mine facilities there, and they should be producing early in 2026 back in Shirley Basin again for the first time in decades. And I mean, at least 3 decades, because I've been here nearly 3 decades. So I had a little hand in that along the way in acquiring that project and seeing it come. But Shirley Basin is going to be a uranium producer again. This is part of the growth. It's exciting. But the nuclear fuel cycle starts with uranium mining, the production of uranium. Uranium is the fuel for nuclear reactors. Then we do something we call conversion, which is to change the uranium from a solid to a gas, to a gaseous form. Believe it or not, you can make uranium gaseous as uranium hexafluoride. It's 1 uranium and 6 fluorides, and that's a gas. You can separate isotopes of uranium in a process called enrichment. Isotopes are 2 uraniums, very similar, but a different number of protons in the nucleus. All right, here we go. Protons in the nucleus. So U-235 is fissionable. It's something that we can split in a nuclear reactor, and U-238 is not. Natural uranium is 99.3% U-238, which is not useful for a nuclear reactor. So 99% of what I mined in my life will go sit and be depleted, useless uranium. And the 0.7% is what we're after. We want to enrich that concentration of the 0.7% for most of our reactors to 4 to 5%. And then for some of the newer reactors, we're talking about enriching up to 20%. Nuclear weapons, we enrich that isotope up to 90 to 95%. So we're, the peaceful use, the commercial use of uranium doesn't have enrichment anything like needed for atomic weapons. But the first 3 steps of the nuclear fuel cycle are preparing the fuel. It's mining, it's conversion and enrichment. Those are the things we're talking about. Then the enriched uranium is fabricated into fuel for the reactors. It's sent to the reactors, it's used. Most nuclear fuel has a useful life of 18 months to 2 years when it's in the reactor. So a fuel rod, a pellet, something small will sit in the reactor and be consumed for 18 months to 2 years before it's used up. Its potential energy has been consumed and converted into energy, and we get what we call a spent fuel rod. Now those spent fuel rods are thermally, to heat, hot and irradiated, which means that they have extra neutrons in the elements, and I'll explain that a little bit more in the what is radiation bit. But those spent fuels need to be cooled down And then some nations, France and others, allow those fuel rods to be reprocessed. Believe it or not, when a spent fuel rod is spent, 90% of the potential energy that could be used to do a nuclear reaction is still contained in the rod. So it runs for a year and a half or 2 years and uses 5% of its or 5 to 10% of its potential energy. And then that rod is waste in the United States because of government policy where it could be reprocessed and we could use that 90%. Again, we could re-enrich, but we don't do that here. So we have to consider waste disposal, nuclear fuel disposal as a part of the nuclear process. But all in all, this slide gives you that whole picture of fabricated fuel, reactor consumption, and then the option of either reprocessing or disposal of the spent fuel. So how does a nuclear reactor work? What really makes this different than other forms of electricity generation? Really, in this case, it's the heat that's generated from the controlled fission, splitting of a uranium isotope 235. That the heat produces steam. The steam turns a standard turbine electric generator. Steam turbines are used in wood, coal, natural gas, and diesel-fired electric power plants. No different. It's just the source of heat. We're not burning something. We're splitting an atom and getting heat from splitting atoms. So this shows you an atom of uranium 235 getting split. And what happens is a neutron, a free neutron, which is a high energy particle, hits that atom. It adds one neutron into the nucleus of the uranium atom, and it becomes very unstable with an extra neutron in there. And it splits into a krypton and a barium atom. And it also throws off a lot of heat. And then it throws off 3 more neutrons. So 1 neutron goes in and 3 neutrons come out. And this is why you can get a continuous reaction. Is each time you split a uranium atom, you get 3 more neutrons instead of 1. It takes 1 to do it and you get 3 out. So you actually have to moderate the reaction with control rods that absorb those free neutrons, or you would have a situation of uncontrolled nuclear fission, which is something we've all seen in the mushroom cloud scenario, right? It's an uncontrolled and nuclear reaction that's allowed to release a lot of energy all at once. So this is a boiling water reactor. This is the typical reactor that's been built in commercial power plants. A couple of things you want to know. Water is used as a heat exchange media. So on the far left, just want to make sure you're looking at it like me. The far left, you see a containment building with a dome. The nuclear reactors inside of that. Water is pumped into that reactor and takes on the heat. The water becomes steam. The steam goes out of the reactor building, turns a turbine, which generates electricity, and which goes to our cities and communities. And then that water, that steam is condensed, cooled again. There's a cooling tower and returned back into the reactor. This was the original design of boiling water reactor. But, the key features is water is heated to steam, and steam exits the containment structure and turns a turbine to generate electricity. If you were burning coal, you would generate heat by burning coal, and that would heat water, which would make steam, which would turn a turbine, which would generate electricity. Not much different, really. Let's boil it down to the nuts. They're not much different except the source of the heat. And this is my pet peeve. This is something that I just absolutely abhor. The image that you see here is not a nuclear power plant. Okay, for those of you who get this, these are cooling towers. These are structures that are used to cool steam, and they generate steam. So that's water vapor being emitted, clean steam being emitted from a cooling tower. And the reason I said, we always see these towers and we think nuclear. That ain't it. That's not, these cooling towers are common to many thermal electric generating facilities, not just nuclear. And every time I see a picture of a nuclear power plant and it's just a couple of these cooling towers, I say, oh, you guys, yeah, oh, come on, let's do some science, right? All right, so the next generation of nuclear power plant became safer because what they did was they put they did a loop of superheated water, and they kept it inside the containment vessel because hot steam needs high pressure pipes, and you're transmitting through pipes, and a steam leak where the steam was in contact with the nuclear reaction could carry radionuclides out. So what they did, they got smarter. They heated up the water into super high pressure hot water and kept it water. And then inside so they have a separate loop, the red loop in there, it goes through the reactor, gets heated up. And then they have a second heat exchanger, which generates steam. So in this case, you have a water loop, a primary hot water loop, and then you have a steam loop. And the steam loop gives you that steam that turns the generator, which generates electricity, and then you cool the steam and you send cool water back in. But there's a level of separation from the nuclear reactor and the water that exits the reactor containment building, and that adds an additional safety feature to reactors. Now we're talking about the TerraPower type of reactor. This is a molten sodium or sodium cooled. So rather than using water to cool, we use a hot metal, in this case, molten sodium, replacing the water as our heat exchange media. The advantage of that is that molten sodium can contain, it has the heat capacity to contain 6 times as much heat as steam. Steam just gets super energetic and it wants to expand as fast as it can. You could put 6 times more heat into molten sodium than you can into hot water. So the heat capacity is incredible. So they have a hot primary sodium loop that exchanges heat to a secondary sodium loop, and hot secondary sodium leaves the reactor containment vessel and goes to a heat exchanger where that hot sodium heats up water, makes steam, turns a generator, makes electricity. Sounds familiar? This is getting repetitive, isn't it? But these are different models of nuclear reactors and evidence that as we went through our learning curve with nuclear, we got safer and safer designs. And that's what we're talking about now. And, for bringing to Wyoming and to our communities is really the next generation of safer designs than the first generation and the second generation. And now we're actually talking about Gen 5 boiling water reactors. They just keep getting safer and safer. The TerraPower unit, again, because I had this slide made. By the way, natrium, we should all know this, we're in Natrona County, it means sodium. Natrium is Latin for sodium. They want to produce up to 345 megawatts in a small modular reactor design, also known as sodium fast reactor. The neat thing about this is that they can store heat in hot sodium tanks, so they don't have to go just straight from generating that heat out of the nuclear reactor to turning turbines. They can actually store it in a hot sodium tank and follow the demand. It's got a load following. So so they have these hot sodium tanks which then exchange to water, to the heat to water, and the electric generation island is actually a separate building. It's not a nuclear facility at all. You're just getting hot steam going across to a turbine. And again, the advantage of this innovative design is that you're going to get gigawatt hour scale energy storage. You can store over a gigawatt of energy, which is about what Casper uses in a day. And it operates at high efficiencies and can follow loads. So it's a really cool innovation in nuclear reactor design. And then there's Radiant. Radiant reactor, it's a microreactor. They want to produce 1 megawatt reactors, one. TerraPower is 345. The Banner reactor, which BWXT wants to do, is about 50. So there's all these different models, and a standard reactor, about 1,000 to 1,200 megawatts. 1,000 megawatts being a gigawatt. Anyways, the fuel is tested and proven. It's called triso fuel. And that's actually what BWXT wants to manufacture in Gillette. They want to use the triso fuel for manufacture of the microreactor here. That's a ceramic coated particle. It actually has shielding inherent in the fuel pellet, and it's meltdown proof. It's been proven that you cannot heat it up enough to melt it down. That's an innovation in and of itself. So it's an inherently safer design. Helium gas is used rather than sodium or water as the heat transfer. And when you get this, you'll really get it. Helium cannot be irradiated. Irradiated means that it takes on a neutron into its nucleus, and helium being an extremely small atom or element cannot take on another neutron in its nucleus. So if helium gas was released to the environment, it would be non-radioactive. Really cool idea. Yeah, I mean, you could irradiate sodium, but you can't irradiate helium gas. It just can't be done. That's science, friends, and that's what science is doing for us. It's finding safer and safer ways to do things. So you have a meltdown-proof fuel pellet and a heat exchange medium that cannot be irradiated. That's great. Air is used to cool the helium. So you have an air jacket around it. And this reactor requires no on-site water wherever it's operating, because it doesn't use water for cooling, doesn't generate steam. It requires no on-site water, doesn't impact anybody's aquifer. And therefore it can be operated pretty much anywhere. In the middle of the desert, in the middle of Alaska, wherever you want. You don't need a water source. You just plug this thing in and start generating electricity. That's what they propose to build here in Casper or Barnum. So let's talk about radiation. Keep this thing moving along. What is radiation? It's energy in the form of either waves or in the form of particles. And when I'm talking about energy, visible light is a wave that's energetic and is actually in the spectrum of what is radiation. You can get irradiated from low wavelength emissions off of power lines. You can get irradiated from radio, cell phones, microwave ovens, wavelengths. Those are all generally large wavelength, not high energy individually. But then you move into like infrared, which is the the wavelength below visible light, and ultraviolet, which we all protect against when we go out into the sun with sunscreen. And then you're looking at X-rays and gamma rays, which tend to be your high energy wavelengths. And those are the ones there you see across the top of this chart. If you can read it, you have non-ionizing radiation and ionizing radiation. And what does that mean? Ionizing radiation is the radiation that has enough energy in it to alter another atom. And that's the damage that can be done. So it's the X-rays and the gamma rays that we're concerned about for ionizing, putting a neutron into another atom effectively. We are swimming in a sea of radiation every day, whether you know it or not. And that's one of the things that creates fear for radiation is we can't see it, we can't smell it, we can't sense it when we're being exposed to it. That's hard. That's a hard thing to overcome. But, I'm about to get on an airplane in the morning. I'm getting out of town. You know why? Because I'm here tonight, right? And I took a chance. No, but every time you get on an airplane, you're getting less shielding from the atmosphere, and you get a lot more cosmic radiation. You get radiation from the sun. You also get, and that's natural. That's a natural source. You also get radiation from the soil and the dirt. There's a lot of radioactive elements in low concentrations in the dirt. You get radiation from the food you eat, bananas and such. 9% of the radiation that you would take in a typical year is from food sources like bananas and irradiated milk, things that we do to, keep germs from killing us. We use radiation to do that, and it's very effective. One of the big sources of radiation exposure is radon gas. Radon gas is short-lived, and when you're exposed to it and you inhale it, it can decay in your lungs and do damage to your tissues, your lung tissues. Another source is medical. So I didn't put this here. Well, yeah, I did. An average US citizen is going to be exposed to 310 units, millirems of radiation in a year. Okay. A medical X-ray is about 10 millirems of radiation. So one medical X-ray could be 10. The dose to the nearest residents, I think there's 2 million people considered in this population, but the dose to the nearest residents at 3 Mile Island, which were attributed to that incident, was 1.4 millirems. Okay, so 1.4 from the 3 Mile Island. I contend that really wasn't a disaster, that was an incident. If 3 Mile Island is a disaster in your books, then please, please, please don't get a dental X-ray. Please don't get a mammogram. Please, because that's 10 times as much radiation as the citizens at 3 Mile Island got. All right. We don't want X-rays to be medical X-rays to be disasters. Not every time. Too many to count. But that's the point about background radiation, isn't it? We are exposed to it constantly. It's not killing us. It's just something that we actually are, the human body evolved in a sea of radiation, and we're accustomed to it and adapted to it. So a little more radiation from a nuclear facility, if you were to encounter it, would be very unlikely to be harmful to you. So let's talk about the different types of radiation pretty quickly. You hear about alpha particles, and that's a large, heavy particle with a little bit of energy. It's electrically charged. It's essentially a helium nucleus. There's 4 neutrons, 2 protons. It has a +2 electric charge. It can be completely blocked or shielded by a sheet of paper. Your skin, your clothes, pretty much anything that alpha particle encounters is going to shield it from you. The risk for alpha radiation is really inhalation. Radon gas, when it breaks down or decomposes in your lungs, you're getting alpha radiation directly to your lung tissues, and that can, if you do it, prolonged exposure can cause damage. Sorry?
Helium's mass is full.
Yeah.
So it has 2 neutrons and 2 protons.
Yeah. What? No, it actually has 4 neutrons.
So its mass is.
It has 2 protons, 2 electrons, 4 neutrons.
That would give it an atomic mass of 6.
Yep. Yeah. I think that's what it is.
Or periodic table.
All right. I looked that up before I put it on the slide. Yeah. A beta particle is faster with more electric, with a single electric charge. It's essentially 1 electron. It's higher energy, but it too can be blocked by simple shielding like a piece of aluminum foil or your clothing. Beta particles can also injure you if ingested, but are unlikely to do much injury to you if just exposed in nature. And this is probably the least discussed type of radiation. Next, you're talking about the wave-like rather than the particle types of radiation. Gamma and X-rays are high energy waves of light at much shorter wavelengths than the human eye can see, and some are at longer wavelengths than the human eye can see. But X-rays and gamma rays can travel greater distances and can penetrate the shielding that blocks alpha and beta radiation. But it can't. But it can be blocked by a heavier shield, like material like lead or steel. So when you get an X-ray, like a dental X-ray, what do? They throw this heavy vest on top of your chest, right? That's a lead shield to protect you from additional radiation. How are we doing on time, by the way? No, yeah,
6:42.
6:42. Holy moly. We're almost done. Four types of radiation. The last type of radiation is neutron radiation. It's a high energy neutron particle with no electric charge. It's a neutron. This type of radiation, is the type that can make other objects, elements unstable, and it rarely occurs outside of a nuclear reactor. It can be blocked. It can be blocked by thick steel or thick concrete. But this is probably one of the more interesting things. So how do we protect against radiation? I've been talking about it as I've been explaining the types. Look, the lady here is putting some sunblock on. That's shielding. She put a hat on. That's shielding. If you're out in the sun too long, what do? Get out of the sun. That's time. If you're close to something that's energetic or radioactive, how do you protect yourself? You get away from it. So time, distance, and shielding are the three principles of radiation safety. Time, limit your time exposed to the sun. Limit your time. The less time a person spends exposed to radiation, the less damage it can do. That's a fundamental scientific principle. Nuclear workers, radiation workers, if you will, have strict limits on how much time they can spend in certain areas of facilities, and that's monitored and that's understood and it's science-based. Keep your distance. Distance is the other, the other thing. The intensity of radiation decreases as you get further away from the source. You ever sit at a campfire? Did you ever step away from that campfire? Same principle. The further away you get, the less heat, the less everything that you'll feel. It works the same with radiation as it did with the heat from the fire. Again, the Nuclear Regulatory Commission in the United States requires facilities with nuclear materials, including uranium mines, the most basic of nuclear materials, to have boundary fences and barriers to keep people, the public, safely away from the source of the material. Those fences are calculated, they're known, the distances are known, that these are keeping the public safely away from the nuclear materials. It's the principle of distance. The final one, which I talked about an awful lot already, is use protective shielding. Different layers of shielding can block all types of radiation. So when you know what type of radiation you're dealing with, if it's spent nuclear fuel and it's irradiated and nucleated materials, you're going to use thick shielding. If it's the sun, you're going to put on some UV40 or UV30 or whatever you choose, depending on how much sun exposure you really want. And you'll put on a shirt or you'll get out of the sun. Time, distance, and shielding. Those are the principles of protection. Finally, last topic, what is spent nuclear fuel? You've seen these pools, the Fukushima disaster, and I'll take that one as a disaster. What happened was the spent nuclear fuel, the electricity that pumped water to the spent fuel tanks failed. They had 3 levels of electricity. When the reactor runs, they got their electricity from the reactor. When the tsunami struck, they had shut down the reactors and they got electricity from the grid, but the tsunami took out the grid. Then they had emergency generators to power the pumps that pumped water to the spent nuclear fuel. But the emergency generators were located too low and the tsunami flooded those and took that 3rd level of design out of the system. And suddenly the spent nuclear fuel ponds, which required water to cool the spent nuclear fuel, was without a source of water. And that water boiled away and hydrogen gas built up in these buildings and exploded the buildings, which spread nuclear material around the neighborhood. That was the disaster. It wasn't a meltdown they actually got to avoid. I'm going to take questions later, man. Thank you.
I guess my son was involved in that. He said they had not updated
Yeah.
that material, their design.
Yeah, it was a design, when you look at the redundancies of design, if they would have located their emergency generators at a higher elevation, they might have avoided this whole thing. Anyways, it was a disaster, and we'll acknowledge that. It wasn't a nuclear disaster in the sense that people were killed from exposure, but it was absolutely a natural disaster. A lot of people got killed by the flood at Fukushima. Um, so spent nuclear fuel as a whole, today's commercial reactors use low enriched uranium. We're talking about, the 4 to 5% enrichment. And that fuel is made of ceramic pellets with uranium inside, and it's stacked inside metal rods. And those are called fuel rods. Fuel rods are assembled into bundles, and the bundles are called assemblies. And those are what's placed into the reactor. This is a picture of an assembly. And in the lower left, you can see how a pellet becomes a rod, becomes an assembly. When the fuel can no longer efficiently produce heat, and there's a pretty tight tolerance on what efficiency is here in a nuclear reactor, it must be considered spent or used fuel and replaced. That usually is it. They run on cycles of 1.5 years or 2 years. Some of the newer reactor designs are talking about 5 years, like the Radiant one. They'll have a 5-year cycle. They'll send out a reactor to a remote site, and it'll run for 5 years without interference, and then they'll come back and they'll swap it out. But spent fuel assemblies are irradiated. They have extra neutrons in them. They have, the material is unstable inside. They need to be cooled. They need to be properly shielded from the environment so that we don't, people don't get hurt from them. So spent nuclear storage is not a new science. This is something we've been doing since the early 1970s or late 1960s. Spent nuclear fuel is contained in casks, which are built in multiple layers of sealed barriers, starting with a metal outer shielding, and then wrapped in a concrete overpack. They're dry storage systems. There's no liquid inside the storage, and it's designed to block radiation and to withstand natural disasters. These are well engineered, and in the history of spent nuclear storage, we just simply don't have this happening. This is not, there is no incidents to point to about the unsafe storage of spent nuclear fuel in dry casks. It can be, they're transportation casks, they're storage casks, but the record for safety on spent nuclear fuel is incredible. So just a couple of facts before I wrap up. The nuclear industry follows strict rules to stop radioactive material from escaping into the environment. It doesn't matter what point in the nuclear fuel cycle you are. Common applications, spent nuclear fuel is stored at close to 75 sites in more than 30 different United States right now. 30 different states have spent nuclear fuel storage stored in dry casks. So we're talking about whether or not we want to do that. We'd be joining a long list. Volumes. The U.S. has about 95,000 metric tons of spent nuclear fuel today. And when our current commercial fleet of reactors, which is close to 100, has outlived their reactor life, then we have about twice that much, about 180,000 metric tons. So that's really actually not very much when you consider that, a ton of coal is, has the equivalent of one little pellet. How much coal and coal ash do we create? The future of spent nuclear fuel storage is really at question. We haven't found a community that wants it. Period. We've gone through Yucca Mountain. We've gone through a lot of debate. But the U.S. government today and the Department of Energy is currently exploring the possibility of consolidating that spent nuclear fuel, not having it at 30 different states and 75 different sites, but at one. If we can just get somebody to agree that this is okay. And I do think it is. So, in conclusion, I turn to George Lemaitre for a quote. He's the originator of the Big Bang Theory. George said, scientific progress is the discovery of more and more comprehensive simplicity. He said, the previous successes give us confidence in the future of science. Of course, Blue Oyster Cult said history shows again and again how nature points up the folly of men. So, what camp are you in? John is going to carry around a microphone, and I'm going to do my level best to entertain your questions.
Right.
So Wayne, thanks for an excellent presentation. So all I hear about is yellow cake. And so how much yellow cake does it take to enrich the pellets that Radiant is talking about?
No, that's a good question. So, Radiant is looking at enrichment at the level of about 20% in the triso fuel, which enrichment is U-235. 20% of the uranium is U-235. So, if you start with, if you want 1 gram, and 20% of it, you're starting with, who's good with math in their head? We're going to go backwards. We need 5 grams of uranium to get enrichment from 1% to 5%. And then, 5 grams of uranium. Yellow cake is about 80% uranium and 20% oxygen. So you got to, once again, throw that up a little bit, ratioed up, but it's the amount of uranium in a fuel pellet is disappointingly little. It's a lot of other protective material in that fuel pellet, but it doesn't take a lot. It's a good energetic source. Hope that helps. But we'll be I don't have the math on how much uranium and how much fuel a reactor for Radiant would take, but it's a small fraction of what a typical reactor takes. And a typical reactor, a 1,000 megawatt reactor, will burn about 1 million pounds of yellow cake in a year.
Thank you. Thank you for all of this information. I think it was the second slide. Safest energy source. So those numbers, do they include, that entire cycle? So in terms of coal energy produced, we're going back to mining. So mining to, production to the facility that actually generates.
Yeah.
So is that the entire cycle for all of those, or is it just on the generation side?
It is. Yeah. So you're talking about the energy intensity of uranium in 1 pellet. Yeah, that pellet delivers that energy over the 18 months that it's operating. Next slide. This. Oh yeah, these are life cycle figures. These are, but really they're unitized. So like the death rate is unitized to a terawatt of power. So it's apples to apples. It's a terawatt of power from nuclear versus a terawatt of power from the other sources. Yeah, that's a statistic that I have referenced the sources on down at the bottom of this slide because I was going to do that myself.
To go to the next slide, please. So on that 1 uranium pellet lasts 18 to 24 months. How long does 17,000 cubic feet of natural gas last?
Good question. Not very long. No.
Or 120 gallons. That's not even 3 55-gallon drums.
That's three. Yeah. Drums. Yeah. Oil drums are 45 gallons. That's a little thing. 44. Very close. But yeah, it's right. It's effectively 3 drums of oil in one. Yeah. Has the same.
18 to 24 months versus 3 drums
Yeah.
of oil will last.
So you put a load of pellets in a reactor and now look, this, it's going to deliver, that pellet is still only delivering the equivalent amount of energy.
Okay.
So no matter what rate it's delivering it in time, it's delivering that much energy.
Perfect. Thank you.
Hold on. I want these back. These are fuel pellets. These are simulated fuel pellets with just safe. Trust me. Plastic, but it looks like a fuel pellet. And there's facts on those cards.
Okay. Question on the
Okay, thank you. Hi.
Waste storage, and I'm particularly concerned about the plant that's proposed for Barnon.
Sure.
The the physics of the nuclear reactors, the reactions are going to produce a lot of short and medium half-life isotopes.
Correct.
And they're basically the same for everybody, is my understanding. And with the spent storage that's going on elsewhere, first question is, of those 75 sites, how many of them are at existing or closed nuclear power plants? Is that all of them or just most of them?
Yeah, it's all the spent nuclear fuel comes from nuclear power plants. And since we don't have a centralized storage location, every nuclear power plant is forced to store their spent fuel at their site.
And that's the concern I've got with the Radiant proposal for Barnon. They won't have the facilities that a power plant has got. The ability to cool,
Okay,
the
yeah.
security, so that you don't get terrorist problems, all that sort of thing. So if they're compelled to store at that site, frankly, I think that's unacceptably dangerous for our community.
Yeah, I think I can help you feel a little bit more at ease. Before that reactor is transported by truck down the highway to our site, the fuel will be cooled. They will not be receiving hot fuel at the radiant factor. So fact number one is that it will be cooled before it comes back to our community. Fact number two, it'll be dry. It is not liquid. There's no liquid involved. It's cooled by air and helium gas. So it is cool and dry, and the TRISO fuels pellets are shielded. They'll be put in shielded vessels and safely managed. I think that the science and the technology and the know-how to safely do that exist. Yes.
Okay, just a couple of things. First off, I really appreciate you being able to get everything that you've taken and put into this and get it on a level that the average person can understand.
Thank you so much.
I grew up within basically sight of Oak Ridge. So I'm kind of familiar with it, but not really familiar with it. And so thank you for doing that. And I just saw where I keep wanting to say BMX, but it's BWX Technologies, correct?
Correct.
They are going to start building their small scale portable reactor at the site of the old Bull Run steam plant between Oak Ridge and Knoxville. So that's, they cleaned the site up, it's ready for construction, so it's coming out there, and I'm pretty sure that it's coming to Wyoming, and I'm good with it, so once again, thank you.
Thank you for the comments and acknowledgement. I do work hard throughout my career. People said, you give good tour, Wayne. You know, I think that's a compliment, but
So Wayne, I want to thank you for an excellent presentation. I learned a lot. My number one takeaway is I've been putting off checking my basement for radon, so I think tomorrow that's going to happen.
that's a good thing, yeah.
But my question is this, as you're probably pretty familiar, Warren Air Force Base is upgrading from Minuteman missiles to the new Sentinel missiles. And that we're behind, and that's a whole nother story. But can you compare the risk, for instance, of having nuclear missiles in our backyard and what's happening at Radiant and Barnon? Or is that risk not comparable? Like, that's my question.
Wow.
Well, it's.
Yeah, that's a tough one.
Thank you.
That's good.
I don't know enough about the security of the military installations. I know that we've been storing nuclear missiles, which are designed to protect us, but it also makes us a target. And that probably concerns me more than the presence of the missiles, but the fact that Wyoming is a target for our enemies because we have these missiles in Wyoming. Truth is, we have a lot of nuclear facilities around, and they're everywhere in the United States, and they've been safely operating. The statistics that we put up about safety include all of these nuclear facilities, whether they be reactors or others. So, you know, I don't know enough about the safety of the Minuteman installations to comment, but I'm comfortable with the safety of and the requirements. Again, I've lived and breathed this for 38 years. I've had to apply for licenses from the Nuclear Regulatory Commission. That's when I lost my hair. 8 freaking years. Bugs, bunnies, climate, weather patterns, weather stations, seismology, geology, hydrology. Everything is studied. Everything is understood at these sites before they can say you get to put it here. They know how far it is, how, you know, to be safe, what distances, what shielding, you know, how much time exposure. They know these things. We have scientific answers for calculating that. And it takes a heck of a team to go through a licensing process, sir.
Yeah, you said the average dose for an average person is 1.3 milligram per year.
310 milligrams.
10 milligram per year. So, I guess I'm trying to think of 2 different things at one time. Let's say we have a dry cask that's loaded, a dry cask that's loaded. What's the radioactivity level at, let's say, 10 feet, 100 feet, a tenth of a mile away?
Yeah, good question. Do you see these gentlemen working on the outside of those casks? Do you see their shielding? Yeah, you do. It's the cask. That cask is designed to block that radiation. The most aggressive neutron radiation is blocked by steel or lead and 3 feet of concrete. These gentlemen are walking outside of the dry casks. You know, they're monitoring any incidental radiation and recording it safely, or they wouldn't be done right outside the cask. Yes.
A bit off topic. What is your thoughts on the President Trump's executive orders in this new 11 design fast tracks that he wants to, sounds like, bypass the Nuclear Regulatory Commission, at least in funding? And what your thoughts are?
No, I don't think he wants to bypass any safety features. I hope not. I hope what he's saying is we can do these, we can man up and we can do these faster. I know there were months when I thought nothing ever happened, but I got billed for time. You know, when I was licensing a uranium mine. Again, the front end of the nuclear fuel cycle, no enrichment, no conversion, no fuel, just uranium. You know, and everything that we had to study, you know, we had to prove, and it would take months, and then suddenly they turn around with 5 questions and said, it took you 5 months to come up with 5 questions on my technical report. That, you know, it took me forever to get the data and assessments on. I think what the president would like to do is fast track licensing, because we have an urgent need, if we acknowledge it, for more electricity. One of the stories that's out there is that the data centers that are proposed for the state of Wyoming are going to consume more electricity than all the households in the state of Wyoming. All of them. And I think that's an accepted fact. You know, I haven't done the math, so I can't exactly prove it or, you know, say, but that's what people are saying. We're going to need more electricity in our state than every house in the state presently consumes. That's a lot. We have an unprecedented growth of electricity in front of us, and we have to step up as a nation and embrace all the power sources. Again, if you thought I was being hard on coal, I wasn't meaning to be. You know, we need coal, we need gas, we need everything if we're going to have an affordable electron coming down that power grid to our homes. Yes, ma'am.
Thank you very much for this presentation.
Oh.
I wondered, obviously the NRC plays a really important role, and I wondered if you can describe to us what has happened to the NRC, whether it's been affected by the cuts that have happened at other agencies or whether it's unaffected things.
Yeah, well, in my industry, the uranium mining industry, the state of Wyoming became what we call an agreement state. And that meant that the state of Wyoming was able to agree with the NRC that the state would self-regulate the uranium mining industry to a standard equal to or higher than the NRC standards. So now the state of Wyoming is audited by the NRC, but the industry participants in the state of Wyoming get to go to the state regulators and get a much more efficient turnaround. So my engagement with the NRC ended probably 5-6 years ago. Governor Meade signed the bill that put Wyoming into an agreement state. So I'm sorry, I don't have a great answer for you.
I don't know a lot about electricity, but I was visiting with a gentleman who worked for Pacific Power. And he was telling me that if you overloaded your wires, they would burn out.
Correct.
Okay, you are going to make all this electricity. How are you going to
Keep the wires from. Yeah.
that will support that
That's absolutely true. We need to expand our electricity distribution infrastructure as we expand our production capacity for electricity. There's no doubt about that.
and he said, oh, you couldn't put it underground.
Yeah, I guess a story I haven't even shared with you. I haven't lived in Wyoming all my life, only the last 28 years. And I've lived here longer by choice than anywhere I've lived in my life. But when I was born, it was in the great state of Wisconsin. I'm a Packer fan, yes, thick and thin. But 20 miles up the road, the Point Beach nuclear power plant was built, and I was a child. And I was born in '65. You could do the math. And in 1970, the first of the two reactors started, and in 1972, the second of the two reactors started. So I grew up in the shadow of a nuclear power plant. All right. My brother, next oldest brother, worked there his entire career and enjoyed a really good job at the Point Beach nuclear power plant. And he and I had lots of discussions because I was making nuclear fuel and he was using it. And we had a lot of discussions. And the one thing that he always came back to is, I am so proud of this company's safety culture. He said, unbelievable safety culture. He said, it's just second to none. He had nothing to do with the safety department, but just for fun, I threw this picture in. It's not the lady with the sun hat, but the three guys in suits. My brother took that picture at the Point Beach nuclear power plant and sent it to me.
Cool.
Yes.
So this one has to do with the tests again. So I heard talk about possibly storing the spent nuclear fuel rods in salt domes underground. So basically, for those who don't know, salt dome is like also it can hold really good oil reservoirs. And I was wondering, is there salt domes in Wyoming that are viable to hold spent nuclear fuel rods?
I'm not familiar with any. That's a great question, but let's probe that for a second. Why do you think we want to store spent nuclear fuel in a salt dome underground?
Well, the fact that there's salt there means there's no groundwater.
That's right.
It's dry.
And shielding.
Yeah.
You're deep underground. We're talking about shielding from radiation and anything. So it's a dry, deep underground shielded, great distance from anybody and anything storage facility. It's just one of the, let's go back to the principles of protecting against radiation. Over here. Hi, Nicole.
Anyway, you mentioned that in Europe they reprocess their spent nuclear fuel. What kind of opportunities could we have for that here if the US changes policy? And For the spent nuclear fuel that's been stored long term, is there an ability to go back and retrieve that for reprocessing?
Reprocessing is something that is known how to do, and they do it in Europe and France. They treat the nuclear fuel and they get the value back out of it. Because again, 90% of that uranium that is in that fuel rod is not consumed during the 18-month life cycle of the nuclear fuel rod. So it seems crazy that we put something in and use it for 18 months and it's only 10% consumed and the 90% is waste. Could we, if we wanted to? Sure. We're going to need people with the knowledge of how to and, you know, a willingness to do it. But reprocessing of spent nuclear fuel is a low priority pet peeve of mine. And Leadership Wyoming class of 2015, Nicole and I. All right. Yes, sir.
I want to thank you. I'm really excited because I've seen things I've taught for 45 years. And that's the point I have.
Mm-hmm.
We need to tell our kids, I don't care whether it's hard or not, you take chemistry, physics.
Yes, and math.
But I'm still a little confused.
Yes.
You said uranium-238 and 235 had different numbers of protons. It's different numbers of neutrons. 92 is the atomic number.
Yes.
That's the number of protons.
Yes.
Helium-6, I'm still concerned. You said helium couldn't be made into an isotope. Well, helium is 4 and 2 of the periodic table.
But it's just,
meaning
yeah.
2 neutrons,
Yeah.
2 protons. Well, I'm confused. I want to find out if there's a helium-6.
It's the new math. I apologize. There's a great deal of pressure on me to stand up here and be the only guy in the room who knows. So I'm going to yield to the gentleman in the front for my misspoken words.
I've been wrong multiple times.
You sound right now.
About 10 to the 5th.
Thank you. Thank you for the science lesson. There's a lot that I had to digest for this. You know that.
Tell your kids and grandkids to take chemistry and physics.
Then they too can be metallurgical engineers with mineral processing.
Thanks very much. You had a couple of pictures there of the portable reactors and the micro reactors. Can you give me an idea of scale? How big are these things?
Well, the microreactor that Radiant wants to build can be truck transported down the road. It literally is. That's the intention. They want it to be the size and scale that you could pull it with a semi tractor down the road. Microreactors. So the Point Beach nuclear power plant, which I happen to know maybe the most about, occupies it. It has 2 reactors. They're 900 megawatt reactors. And they occupy a site that's about 70 acres, 70. The entire property of the Point Beach nuclear power plant, it sits on Lake Michigan in a deep water area. And the entire property is about 1,200 acres. Last time I went back there, they littered that 1,200 acres with solar panels. They're co-producing solar and nuclear right into the grid at the same spot because they needed that buffer zone for their property. So they have that 1,200 acres buffer and they just using it to generate solar power. TerraPower, it's probably, a 400 or 500 acre site, if that, and that's a 350 megawatt, reactor and all of the buffer around it. So, we're really talking about small footprints compared to other power sources. Does that help?
You can fit 3 of those containers in this room.
3 of them, yeah.
Yeah.
3 megawatts of electricity generation in this room. Oh, cool. Yeah.
So my question is related to your background with the reliance of the uranium industry right now, currently with some of our less favored nations. Is the U.S. uranium mining industry or the industry itself, are they capable of recovering that momentum that they had at one time.
Fantastic. That's one of the slides that I took out because of time. So thanks for asking it. How did you know I would think about that? The state of Wyoming, in the last decade is, the uranium industry's been on its heels, but it's come back because there's a renewed interest in nuclear. And, we were producing a couple 100,000 pounds of uranium a year, really incidental to existing, rather than with a concerted effort to produce. This year, we're going to produce over 1 million pounds, and we have a licensed capacity to produce about 20 million pounds a year in the state of Wyoming, which means facilities that are licensed. Not all of them are constructed, but we're doing that. We could produce 20 million pounds a year in the state of Wyoming. And the U.S. uranium production industry is probably 25 to 30 million pounds of licensed capacity. Set that against there's 90 to 100 operating nuclear reactors. And that's a very dynamic number right now because plants like the Palisades nuclear power plant on the Michigan side of Lake Michigan, across the lake from where I grew up, Palisades is being reactivated. It was retired and they're reactivating it. So, and a number of the nuclear reactors are 3 Mile Island is coming back to life. We actually have an increasing number because of retirements are being unretired. God, don't tell me that. I'm retired. Anyways, so we would typically consume about 50 million pounds of uranium in the United States. So even if the mines and the license capacity that we have today was fully operating 25 million pounds in the US or 30, we're still reliant on imports of uranium. We're reliant on imports of conversion and enrichment. We have a conversion facility. We have a company that's expressed an interest in building a new conversion facility for the first time in my career. And we have enrichment in the United States, but it's foreign owned. So we do have a couple of years ago. Right. Well, we have low grade uranium deposits, so there's a higher cost, but the market's good right now. It is good. And that's why they're ramping up production.
What countries would we rely on for the extra material?
Canada is one of the world's biggest producers. Kazakhstan, which is in the sphere of Soviet influence or Russian influence, is the world's biggest producer and exporter. We have African nations, Australia. We have a number of friendly nations that we can rely on, and I think our fuel supply, our source of uranium from friendly nations is secure and enough. If we were to go to war, and we did actually ban and prohibit importation of nuclear fuel from Russia. So we're not in a very friendly way with Russia right now, and we were relying on Russia. And one of the most interesting facets, which you probably hear about, is that the highly enriched the fuel, the 20% fuel enrichment, we don't have that capacity in the United States. That the fuel that Radiant wants to use and the fuel that BWXT wants to generate or fabricate is 20% enrichment, and we presently do not have a commercial or government means to produce high assay low enriched uranium. That's what that's called. 20% is HALEU, high assay low enriched uranium. Next to you is Adam. Do you have a question? Hi.
Yeah, mine's more of a side tangent question. Have you ever heard of the natural fission reactor that is in Gabon, Africa, where there was an actual natural fission reactor?
If your uranium concentration is strong enough in nature, that can happen, and it did in Gabon. And yes, there is this. I mean, we didn't create nuclear power; we observed it and then duplicated it. Yes.
The extra material that has to be shipped in from other countries, what's the safety factor with that?
Well, we've been, we've had a commercial nuclear fleet since 1970s, late 60s, 1970s. And we've been transporting nuclear fuel around the world, shipping containers, ships. It's all considered and thought out and safe. You don't hear about accidents. I'm thinking that's not because they're burying it. I'm thinking it's because it's not happening. And over there, maybe one or two more, and then I'm gonna have a drink.
Can you give us an idea, footprint of the plant? How much energy out? How much housing? And how much final product storage area? And then on top of that,
Are you talking about the radiant?
whichever one you choose, the one we
Okay.
want up in bar none.
Yeah.
How big of a footprint for production? How big for storage of spent material?
Yeah.
And then how many houses would it actually energize? On top of that, are they gonna build it and never give it to the local community? But say, hey, let's put in a
Yeah.
AI facility,
So
and the local communities never get that power.
the radiant business model is unique in that what they're proposing to do is manufacture portable units to ship to other locations to be operated. So they won't be operating a nuclear power plant in bar none. They're just manufacturing them to be operated elsewhere. These units, these once fabricated, again, they're saying the life of the fuel. This is just public information that I've gathered by my research, but the life of the fuel should be about 5 years. So if you deploy it out to a remote location that needs electricity, they're saying it can power a military base in a remote location. Military is very interested in this because they don't have to transport diesel in to power diesel generators. That's a big logistics issue in a remote location. You can just bring one truck in and power that base for a long time, or two or three, and line them up and run them in parallel. That's cool. But after 5 years, that reactor is going to be turned off. It's going to be cooled, and it's going to be shipped back to the factory, refueled, and sent back out into the field. So the spent nuclear fuel that comes out of that reactor from Radiant, one reactor, they said the size of the fuel is about the size of a propane tank that you use with a gas grill or a fire pit or something like that. So the volume of spent fuel that we're getting back after 5 years from any given reactor is very, very small. It's going to get stuck in a dry storage cask and shielded from the public. And I'd imagine they don't need very much of a footprint for that storage facility, but it will be studied to death by the NRC and others before they have the right to do that. They can't just do it because they say they want to. They've got to get permission, and God, that's a hard process.
It's building. Yeah.
Correct. And then bringing the spent fuel will come back, and it'll be kept here until the U.S. government gets its poop in a group and gets a consolidated spent fuel storage site in the United States. One over here.
So I kind of feel that this conversation has been tilted to in favor. Do you have anything negative to say, like the subsidies, or that the infrastructure is going to make our rate go up on electricity?
Oh, I don't think that having a manufacturing facility in our community is and having, just because it's generating a nuclear power plant is going to impact our costs of electricity. That's not power that's going into our grid. That's our local grid, and it's not power that's going to our utility who supplies us the electricity. I think that's a complete misunderstanding of how things work to suggest that our electricity rates are going to go up because a manufacturing plant is built in our community. I'm upfront. I've been in the nuclear fuel cycle and industry for my entire professional career. I've studied radiation safety. I've taken radiation safety training every year for the last 38 years. I pretty much ace those tests when it comes around. I'm comfortable with that stuff. And, you know, that's me. So yeah, I mean, if I have a bias, it's that my background, my life experiences tell me that this is going to be okay.
My understanding is that the spent fuel is going to come back inside the reactors and going to be extracted here and placed in the casks here. And my concerns with the radiant plan are twofold. One is potential for accidents in the extraction and putting them in the casks. That ought to be something that can be managed and properly regulated. And then my concern is the ability to store the volumes that they will eventually get here and store it safely. That, because it's so different from the nuclear power plant circumstance, I think is something we have to really be careful about. Because even though it's a small volume, that volume is very good.
So I'm surprised, but I guess I'm going to have to put you in the Godzilla camp. And not that you trust science or trust the regulators that the government has put in place to study and ensure that everything that they do at their facilities, because it's a nuclear facility, is done safely. If you don't trust the government, what are you doing in it, Senator?
Absolutely.
I've been in the government long enough now.
All right, so let's go ahead and wrap this up. I want to thank Wayne Hiley again for coming here and sharing all of his experience and knowledge with us. If you have an identification card, you can either scan the QR code or you can fill it out by hand on the back and just drop it in the basket over there. And we thank you all for coming, and please, we will send out another notice when the next one is, and we hope to see you at the next one. Thank you and have a good evening.
Hey, quit asking for golly.
Thank you. Yes.